Hey guys, I'm Blitztage, and yesterday there was a Codeforces round CF767. I gave the Div 2 version of the round, and I would like to discuss the solutions for the same, give my intuition regarding how to solve the problems. I personally secured 38th rank in the contest and solved problems A, B, C, D, F1, and F2. So let's discuss these and I'll try to give some intuition. So the first problem is pretty simple. It says that you want to download more RAM. It doesn't happen, but let's take them for their word. So basically, we have n different pieces of software that increase your RAM. The IH software requires that you already have AI amount of RAM with you, and it will give you BI GBs of RAM more. And you currently have KGBs of RAM, and you want to have the maximum RAM that is possible. So there is a very trivial O of n squared solution for this problem. That let's say there are n iterations, and at each iteration I go through all of the different softwares, and if any software works, I just use it. The point here is that a software can only increase your RAM. It is not going to decrease your RAM. So if you're able to use a particular software in the fifth iteration, you can use some other software. You can use some other software in the fifth iteration and use this earlier software that you wanted to use in the seventh iteration. So you're not losing anything by using a software at a particular iteration. So for an ON square solution for a particular iteration, you just look through all the different softwares. If any of the softwares has a requirement lesser than what you already have, you just use it and increase your RAM. And do the same for n iterations. After n iterations, the maximum amount of software that you can use is n. Like each software a single time. So after n iterations, you should get the final correct answer. There can be no more increment since you would have used a maximum of n softwares already. I personally used a O of n log n solution here. That is because if you're able to use a software which has a higher requirement, then you can definitely use a software which has a lower RAM requirement. So I just store a and b in an vector first, and I then create a vector of pairs in which the first element is a of I, and second element is b of I, and then I just sort the vector of pairs. On sorting a vector of pairs, what happens is for you the elements primarily get sorted using the first element. So the shortest first element is the shortest element in the overall sorting of the vector of pairs, and if AI is same, then it gets sorted by BI. And then I check for all the elements. So I just want to greedily choose the lowest like smallest RAM requirement possible, and since my RAM is increasing, it is possible that I might get some software which has a higher RAM requirement. Suppose I have a software which has requirement k plus 1, so I cannot take it initially, but if I use a software which has a lower RAM requirement and gives me 1 or 2 GBs, then maybe at a later iteration, for the later element, by the time I reach the later element, I might have the RAM requirement for them. So once you find an element which has a RAM requirement higher than your current RAM, you instantly break, because all of the elements after it are going to have an even higher RAM requirement. Else you just accept that, you just use that software and increase your RAM by the increment that it gives you. And finally, you just print out what is the maximum RAM that it is possible for you. So this was the A problem. So let's move to the B problem here. Okay, so B is an interesting problem. So you have integers in an entire range. Say L is 3 and R is 7. You have all the elements. So 3, 4, 5, 6, 7, and you want to perform certain operations on the array such that only one element is left, and no, you want to perform such that the array is shortened or the array is constant. You can perform an operation at most k times. What that operation does is it chooses two numbers, and it removes them and inserts their product. And you want to find out a certain shorter array after performing these operations such that you take the lowest amount of operations possible, and the GCD of the remaining array, like GCD of all the elements, is not a 1. So an interesting fact to observe here is that all of the elements, they are not random elements. So you won't have 3, 6, 9 here, in which case all of them have a GCD of 3. They are consecutive elements. So if they are consecutive elements, so you only one third of the elements, maximum of one third of the elements will be divisible by 3, maximum of half of the elements will be divisible by 2. So you need to understand that suppose if I have say 3, 4, 5, 6, 7, 8, the best approach here is to take all the odd elements and multiply them with some even element. It is because uh, 2 is the most frequent divisor. Like every second element is a divisor of 2. So if you just handle all of the odd elements, just multiply them to any even element, the product of an odd and even number is definitely going to be even, and the GCD of all even numbers is going to be 2. Uh, you need to understand that we are using this fact just because all of these elements are in consecutive order. So we definitely know for sure that every second element is divisor of 2, uh, is divisible by 2, every third element is divisible by 3, and so on. So 2 is the most frequent element, hence we are just making sure that GCD of the array is 2, in which case we are just multiplying all the odd elements to a certain even element. So there are some cases, it's kind of interesting cases. Let's just look at it. Okay, try to maximize the size. So so I just input L, R, and K, which are L is the left boundary, R is the right boundary, and K is the okay. So K is the amount of iterations that they allow you to do. So we need to find out all the odd elements. So if there is like a certain amount of odd elements, we are going to just add them to certain even like some even element. We just multiply them with some even element, and the overall product still remains even. So there is this fact that from 1 to r, the number of odd elements is r plus 1 by 2, where like by 2 is basically the floor. So like suppose if r is equal to 7, you have 7 plus 1, 8 by 2, 4. So you have 4 odd elements. For 6, you have 6 plus 1, 7 by 2, which is 3 odd elements before it. So for 6, we have 1, 3, and 5, which is 3, and for 7, we have 1, 3, 5, and 7, which is 7. So we want all the odd numbers till r, which is r plus 1 by 2, minus all the odd numbers which occurred before L. So for L, we would have had L plus 1 by 2, but we want all the odd elements till r, which is r plus 1 by 2, minus all the odd elements till L minus 1. Because anything after L minus 1 and before and or equal to r is going to be included in our range. So we have r plus 1 by 2 minus L by 2. This is the number of odd elements. Now, if r is equal to L, that means that you have just one element. So say you have just one element 13. So it definitely has a GCD of more than one, even though it is odd. Since there is no even number adjacent to it, you won't like the numbers adjacent to each other are the ones which will be co-prime. So if I have 13 and 14, their GCD will be 1. But if I just have just one element, its GCD will be itself. But there is another exception to this exception, that if R itself is 1, so you have just one element which is 1, then the GCD will also be 1. So this exception I'm tackling with the fact that if R is equal to L and R is equal to 1, which means that R is equal to L is equal to 1, then so I'm just using this expression that no means that I just print no and I just return. So I don't want to print return every time, so I have this macro. So if r is equal to L and r is equal to 1, then I just print no and just return. If now k is the number of operations that they give us, and each operation removes one odd number. So if my number of operations is greater than equal to the number of odd numbers that I have, then my answer should be yes. And as I explained earlier, if r is equal to n, in any other case other than r is equal to 1, then also the answer will be yes. For example, r is equal to L is equal to 2 will also give you yes. R is equal to L is equal to 13 will also give you yes. Yes. So this is the only case in which you get yes, and in every other case you cannot possibly extinguish all of the odd numbers. Hence the answer that you'll get is no. So this is problem B. So now is problem C. I seriously thought that problem D is much simpler than problem C. But if problem C is given earlier, let's discuss problem C earlier. Okay, here we are. Okay. Okay, so we have been given an array A, which is n non-negative integers, and we want to create a new array B. Yeah, so I hope you have read the problem, and we want the array B to be lexicographically maximum. So lexicographically maximum itself includes an idea of greedy, because you want to have the maximum, like the highest max that is possible. So one clear idea here is that suppose I have a certain array A. So let's assume that this is my entire array A. and it has a max value of b, you know that the max value of an array does not decrease if you add another element, because max is just if you have all elements from 0 to b minus 1, adding a new element doesn't reduce your max. So we want to have a max which is equal to the max of the whole array, because that is the maximum max we can have. There is no point having a lower max if a higher max is possible, because we want a lexicographically maximum max. So the greedy approach here would be to choose the lowest index such that it has a max equal to b, because the elements after that are anyway wasted. So if we are not going to use them, why do you want to include them? We may use them later for some other purpose. So we want the first index such that the max is equal to b. And after that, we just output b, so our answer is b. After that, repeat the same process on the right hand side. Have the max of whatever is left, and you want to greedily choose the smallest index such that the max of this region is equal to the max of the suffix. If it is not equal to the max of the suffix, we have to include another element, possibly include the whole region, such that we get the highest max that is possible. So let's say the value of max is c. So you apply the same procedure to smaller and smaller and smaller regions, suffix regions, um, till your till you use up all of the elements. So in general, this would be like a n square solution or something, but it is not allowed to. Like if we just find out the max of suffix every time, and then calculate our max every time, and for every small region, every suffix region, it would be an O of n square solution. So we will have to find out tricks such that we can have this solution as O of n log n. So there are two different tricks that I have here. One was what I used in the contest, which I think is slightly longer and lengthier, but that was the only one which came to my mind. Let's have a look at both of the solutions. So this is the first one. This is what I implemented in my contest. Okay. So what I do is, okay, let me just go back to. I'm going back to Jamboard here now. So let us take a example over here. Let's say this guy. So 2 2 3 4 0 1 2 0. This is my example. So what I'm planning to do is, for I have been like they have mentioned that AI is greater than equal to 1 and less than equal to n. So you can so what I'm planning to do is I'm going to maintain a set of vectors for each of the particular elements. For example, I'm maintaining a set for 0 1 2 3 4, and I'll maintain them for, since n is 1 2 3 4 5 6 7 8, n is equal to 8, the maximum mix that is ever possible is 8. So I'll maintain a set for all elements till 8. Let's just have another element 9. So it is basically for implementation purposes. Since I know that the max will never reach 9, uh, maybe I just like stop somewhere unnecessarily. So I'm just including one element extra for like implementation purposes. So I see that so in this set I'm going to store the indices of where that element is located. For example, 2 is located at position 0, so I add position 0 to list of set of 2. Similarly, I add 1 here. 3 is at the second position, 4 is at the third position, 0 is at the fifth position, 1 is at the sixth position, 2 is at the seventh position again, and 0 is at the eighth position. Okay, so this is the general vector of sets that we get. Now, what my idea over here is that if I want the max to be 5, the earliest index at which the max is equal to 5 will be the maximum of the first of all of these indices. Because you would need, for the max to be 5, you would need 1 0 1 1 1 2 1 3 and 1 4. So if you require one of each particular element, we will take the earliest, the set stores the earliest index at which it occurs, and we just see the maximum of this. So it is 6. So the latest a particular element, suppose I want to max 5, so the largest index that I have to wait for any of these elements 0, 1, 2, 3, 4 is 6. So if I wait till index 6, I'll get one of these guys. And we require one of each of 0 to 4, because we cannot afford a max which is lower than 5, since we want a lexicographically maximum max. So I think explaining by the code would be a slightly easier thing. So I'm just the set is known as val, and it stores the indices of the particular occurrence of the particular element, so AI. So I just insert all of the elements of the vector into their particular set. Now what I do is till 0 is not empty. So basically understand the fact that if I have ones and twos and threes and fours, when I don't have a 0, my max is always going to be a 0. So if I want the max to be non-zero for a certain certain region, I would need to have a 0 at least. So this while loop is only going to run till I have zeros. After that, I'll just assign zeros later. I'll talk about this later. So till the point I have a 0, what I'm going to do is I'm going to go from 0 to n plus 1. I'm so definitely won't have n plus 1 ever because AI only has a maximum of n. So what I'm going to do here is n plus 1 is just for implementation purposes, so that I definitely know that I will get I will be empty over here, so that I can definitely add another answer. So the point here is that we want to know how many till which position we have already used for our previous iteration. So int worst is the worst index that I have already used for a iteration before. So let me tell you basically how an iteration works over here. So what is going to happen is for the first 6 iterations, this is going to be one particular region, and after and it's going to consume all of the elements in this region and going to give me a mix of 5. Then the last 2 elements are left. They are going to be another region, and I see that the max of these two guys is 1. So just add another 1. So this is a particular iteration of the while loop. A particular iteration of a while loop consumes these amount of elements. So what I want to do over here is worst is the worst, like the highest index that has been used by a iteration before. So when I'm starting this loop, the loop for 2 commas like 2 and 0, the last 2 elements that are left, I need to know that I have already used all the elements till 1. So even if say I use the first two for the first iteration, but I cannot use the second two. Why can I not use the second two? It is because since I've consumed all elements till 1, even if some element had been repeated before 1, you still use it because it is not after the worst element. So what happens is when I eliminate the beginning element of each set, I remove 5, remove 6, remove 0, remove 2, and remove 3. One is still left. So it is possible that you go to the next iteration and see that you have one still left. You have a 2 still left. But you also have to remove this one because it is before your worst, and hence you cannot take it. So what I do is till my set of indices gets empty, or the slowest element is less than worst, I'll remove the lowest element because it is completely useless. I cannot use something which is before worst because it has already been consumed by the regions before it. So if now the val of I is empty, I have no indices. So let's say this occurs for I is equal to 3. That means that I successfully found a 0, successfully found a 1, successfully found a 2, but I could not find the 3. So what I just do, that means that the mix of this particular region is 3. So I push 3 into the answer and break. And what I do is I don't and now I want to update the worst. So for the next iteration, I want to know what is the new worst, what is the new index before which I cannot take any element. So I just checkmax is another function that I use, which just sets uh, cur w to max of cur w comma this guy, and I just erase all the elements that I have used. And my worst is I have set it back to curw. So curw is basically the worst that I found in this iteration, and the worst is that is curw is the worst element that I found in this iteration, and the variable worst stores the worst element that I found in all the iterations except for any ongoing iteration, because we don't care about any ongoing iteration. We just want to know whatever has been used by the previous iterations. Now after this, let's go here. Let's go to the back to the Jamboard. So this would give you an answer of 5 comma 1. But say I have another element, say 17. So and another element 13 and another 17. Three more elements. So these elements are practically useless. You're never going to have any mix which is greater than 0 for it. So for each of these elements, any element that you get, any extra element, just add 1 0. You just pick them as a singular region. And since none of them is going to have a higher element, there is no point combining two of these, combining three of these. The mix will be 0. So we better have as many zeros as we can. So at the end of this loop, I hope I'm recording it. Yeah, everything is fine. Yes. Yep. So at the end, what I do is I just look at if any of the sets has some element left which is higher than worst. Again, you want to remove all of the elements which are lower than worst since they have already been picked by the region before. If anyone has a value higher than worst, we just add a 0 for them and we just erase them. So we'll add as many zeros as many elements are left. And then this prints the size of the answer and this prints the whole answer. This is the solution. So this is one of the variants of the solution. The other variant is also pretty interesting. Let's have a brief look at that. Sorry. Okay, so this is the second variant of the solution. What we want to do is in this variant we just calculate the max for each of the suffix. So let me go back to my example here. Okay, let's copy this test case once again. 2 2 3 4 0 1 2 0. So what we do is we want to know the max for any suffix. I explained the method earlier as well, the idea earlier as well, that we want the max of a particular suffix, we want the max of a particular region, and we want to find the lowest index such that we could achieve that max. So we have to understand that the region that I mentioned earlier is definitely going to be a suffix. You are not going to consume index 11 before consuming index 7 in some particular region. So if we just pre-compute the max for all different prefixes, then we could have a easy way later. So for this, I would put a link for a video by Peltorator, which just shows you how to compute the max for various sets and various indices, say suffixes. Everything is included in that. So basically, what you do is you have a complement set. Complement set stores all the elements which are not present in your current set. So for example, if you have 0, 2, 3, it stores everything which is not 0, 2, 3. And you know that the max can be n plus 1. If you have n elements, you cannot have a max which is larger than n. The maximum max that is possible is n plus 1. Sorry, it is n because you can have 0 to n minus 1. So the maximum max possible is n. So it has all of the elements which are not in the set. So you will have say n is equal to 5 over here. So you will have 1, 4, 5, 6. So this is your complement set, and this is your, okay, I need to go back to jump. Sorry for this. So this is your complement set, and this is the set that you have. So you store this complement set, and you also store a map. Your maps tells you how many of a particular element you have. So if I have 1 0, I will store map of 0 is equal to 1, map of 2 is equal to 0, is equal to 1, map of 3 is equal to 1. So if I get another 1, I will just increase it to 2. So what this does is that it tells you the max in log n. It adds an element to your set in log n, and it removes an element from your set in log n. So since we are using sets, the add and remove log n part should be like pretty clear to you because set add and removes are in log of log n. But the calculation of max in log n is pretty like it's slightly difficult to understand, so I would recommend you to watch that video. So this is the array going from n minus 1 to 0. It calculates the, so at every iteration what I'm doing is basically I'm adding another element. So adding another element means removing it from the complement set. And this is how, using the same technique that I mentioned earlier, you get the mix. Okay, this is the, and you have to do the same thing. You have to do complement set. You insert all of the elements because before you so now yeah, okay, so this calculates the suffix of mix. These are first part. And now, as I mentioned earlier, you want to greedily choose the smallest index such that the max of this region is equal to the max of the suffix so that the remaining elements can be used to serve some different purpose, some later purpose. So I maintain a complement set here. First, the complement set would contain all the different elements. Then I have a map, as I mentioned earlier, the same technique as in Peltorita's video. And for every element, I try to check if it is there in the complement set. If it is there in the complement set, I'm going to add one of them now. So if it is there in the complement set, I'll remove it from the complement set and add one to the map. And if I find out that my current max, so current max is always given by the first element in the complement set. If it is equal to the overall max that I want for this particular suffix, so start is basically the start of your current region. So if you are getting the max of your current region by only including elements till element I want to say that add the max of the entire region that you have and consider this to be the region. So my next region is going to start from I plus 1, and now I want to remove all of the elements which existed before start, before the new start. Say I have 0, I have a 0, I have a 1, I have a 2, and before so my complement set would just be 3, 4, 5, 6. But now for the next iteration I want a completely clean slate. I want all of the 0, 1, 2, 3 to be in the complement set, and also their map value should be 0. So what I do is from the last start to this start, all the elements that were used, all the elements that I found, I am going to remove them from the map. And when I remove them from the map, if they get to 0, I know that they have to be included back into the complement set. Actually, this might be a bit difficult for you. Maybe you don't understand this right now, but this is a standard technique which has been linked in the description. So this tells you just how to get a max in log of n. And once you know this technique, you just want to greedily choose the first element. And if you keep on doing this, you would have the correct answer. You greedily choose the first region and you keep on doing it, and you add the best max for the remaining region to your current answer. When I print answer.size, I print answer. One interesting thing I just found out is that if you want to print elements of a set and you have some extension, like you have some function to print elements of a vector, you can just make a vector which includes all the elements from the start of a set to end of a set. You can just use it to print if you want to print a set pretty quickly. So this was C. Then I spoke for a long time for C, but I felt it was an interesting problem. It's a difficult problem. I think this was a problem that I took the largest amount of time in. Not F1, not F2, but C. So D. Comparatively, D is a lot easier. D is a lot more easy. So D basically states that let's go to D. Let's read D for a moment. Where is it? Yeah, yes. Okay. So what did D say? So D says that I have n strings, n non-empty strings. The size is at most 3. This is the most important point here. And you want to find out if I can perform a subsequence of S such that the subsequence, the concatenation of all the strings in a subsequence gives you a palindrome. So for example, let's take a simple example over here. So let's say this ZX ABCC ZX BA. So if I just choose AB and BA and concatenate them, this is yes. This is a palindrome. So this gives us a yes. We can just choose even this to CC. This is yes. So you need to understand one fact here. One interesting thing over here is that if a string has a size of 1, just say I have a stray element. I just have a stray A, stray B, stray Z. I will not take anything else. I'll just take these. I'll just take one of these elements. I'll just take an A and just say that is the only index that I want, only string that I want. And since since a string of size 1 is definitely going to be palindrome with itself, you can just end the process here. So basically, this problem just boils down to case work. So you can have a size of 1, size of 2, and size of 3. You just take all the cases that they have mentioned. So if you have a size of 1, just instantly print yes. Don't even think about it. If you have a size of 2, if it is a self palindrome, for example, CC, the reverse of CC is also CC, and both of these are equal. If both of them are equal, you can instantly print yes. So if it is a self palindrome can be represented by if S of 0 is equal to S of 1 is equal to, then print yes. Else, suppose I have BC. Now the only way BC can work is if I have a CB before it. So you just pick the earlier CB, I pick the current BC, and I just output only these two. Okay, so that is one way which can work. So what I do is I reverse the string. So if this my current string is S, I reverse it to get T. And I see that if I see that T has already been used earlier, then I instantly print yes. One interesting fact over here is that you can also, instead of CB, you can also have something like, let me just erase this part here. If you have something like CBA or CBD, even adding BC to this works, because this element, since you would have an odd number of elements by including one string of length 3 plus one string of length 2, you would have a total string of length 5. So the middle element won't even count because it would not have any corresponding element that it would have to match. So what I do is I just reverse the string to get CB, and then I add all of the characters from A to Z. I check if CBA is there, CBB is there, CBC is there, till CBZ is there. If any of these guys are present from CBA to CBZ, I instantly say yes again, because I can add, say I get CBD, so I have CBD and I add BC. So this is definitely going to be palindrome again. So first, if I check if the reverse element is if it is a self reverse, then I check if the reverse element has already been already existed, and then I add one element, and then I add one more character to the end of the string and check if any of these have occurred earlier. And by the logic of this CBDBC example, all of these will give you an answer of yes. Similarly, I think maybe you can pause the video here and try to understand the third case here, case of size equal to 3. But it is similar to this. So if I have, say, an element AZB, I would really like if there is something like BZA before it. Because you clearly know that concatenating these two elements will definitely give you a palindrome. So just reverse the string. So if this is string S, reverse string S, and check if uh, the reverse string T is present. If it is not present, what you can do is remove this last element. Okay? We do not need this. If we just have BZ, we still would have an odd a string with odd size, which is basically BZAZB. So even if we remove the last element and check if so what we do is we just pop back the last element, and if we still find and now if we find that T is found in your map. Yeah, I'm using a map to store the frequencies of all the strings that have occurred earlier. So now if we see that T has occurred earlier, we can still print out a yes. If none of these cases work, I claim that the answer is no. Because any cases, like say you add 5 strings, add 7 strings, those are redundant. Like, so if I add 5 strings with size 3, size 2, I can always show you if if an answer exists with 5 strings concatenated. I claim that I can always show you an answer with 2 strings or 1 string, 2 strings concatenated or a single string there. You may want to like think about this more and try to prove it to yourself. So let's look at let's look at my implementation for the same. My video is going long. Like, this is my first video, so I think I'm over explaining things. But I think over explaining is definitely better than under explaining. Let's go, baby. Okay. Is it like it's too large, too large. Yeah, this is fine. Yes. So I just print I have the vector of strings with myself, and the current string is string yes. If it has a size of 1, you instantly print yes. If it has a size of 2, if it has a self-reverse print yes, then reverse it. So I just reverse this. All is another function that I use. So all is another macro that I use, definition that I use. If I find the reverse, it's yes. Then I add another element over here. As I mentioned earlier, if I find any of these, the answer is yes. For the case of 3, if it is a self-reverse, I again select yes. If I find the reverse, I select yes. And then as I mentioned earlier, I pop back the last element. If I still find T, I still print yes. And after this, I just insert the newer string that I have got. And if I cannot find anything after the entire iteration, my answer is no. This is D. Now after D, we move on to F1 and F2. Those are pretty challenging. I think F1 is pretty easy. I think F1 should be easier than C, according to my honest opinion. but F2 is pretty difficult. I think. Let's go to F1 and F2. I think the rating of F1 is going to be higher because many people went to E rather than F1. Okay, so I hope you have read the problem. So I'm just going to solve it by DP. So what my DP states is that DP of I comma j is when I have I turns left and I can have j negatives possible. I'm thinking according to the perspective of Bob, because like Bob wants to have the lowest sum possible, and let's say if I was Bob, what I would do is I would want to keep as many negatives at the end as possible. So I'm thinking in the perspective of negatives rather than positives. So I turns left and j negatives left. This is DP of ij. Let's pre-compute some. Let's look at some base cases over here. So if I have DP of I comma 0, one thing you need to understand is that Alice knows every move that Bob has made. So Alice knows if Bob has any negatives left or how many negatives he has left. Alice knows everything. So if Alice knows that Bob has 0 negatives left, Alice would just output the maximum possible number every time. So it would be k times I. Another thing is if you have dp of 0 comma j. So okay, let's not do dp of 0 comma j. Let's consider dp of j comma j. So if Alice has j turns left and Bob has a possibility that all of these can be negative, then the dp would be 0 because Alice is forced to give zeros now. Because any positive number she gives would be converted to negative by Bob. So 0 is the best option for Alice now. So if you have these two base cases, you just need one relation for the dp. And if you get that one relation, the problem is basically solved. That one relation is pretty interesting. Let us consider a particular case, say dp of I comma j. What I'm going to say is that dp of I comma j is that when I have I turns left with j negatives possible. So to motivate this effect, I would like to give you dp of 2 comma 1. So what do we claim that the value of dp comma 1 is going to be? I claim that it is going to be k by 2. Let me tell you why. Let us say that the when two turns are left, Alice gives a number which is a value of q. We know that q definitely has to be less than equal to k. So let's say she gives a value q, and Bob chooses to use his last negative on it. If Bob chooses to use his last negative on it, minus Bob will gain, like the answer will be reduced by q. But then Alice would have Alice would have the last turn to like free to put anything. So like all the negatives have been used. So Alice knows that Bob has to add the one that is left. So she's going to give the maximum possible element, which is going to be k. Else, if Bob chooses to add it, then he's going to have q added to the sum. But now Bob still has that one extra negative left, which he will use because there is just one turn left, and you are definitely going to use it. You're not going to add if you have subtracts left. So Alice is forced to give a 0. So what you want to maximize is the minimum of minus q plus k comma q plus 0, where q is between 0 and k. So for any of such I don't know, calculation of optimal conditions, you will have minus q plus k is equal to q. Basically, you will have q is equal to k by 2. This is because both of these values will be k by 2 here. So you can plot it as a line. For example, q would be this line and minus q plus k would be this line. So for the for you to have the lowest minimum, you would have to choose this point, which is both of the values are, which is q is equal to k by 2. If q is equal to k by 2, both minus q plus k is k by 2 and q is also k by 2. So now let's get to something useful finally after all of this math. So what I find out is that dp of I comma j is equal to dp of I minus 1, since you will have one lesser term irrespective of what you do, with j negatives left plus dp of I minus 1 with j minus 1 negatives left and y2. This is the relation for the dp that I have. And once you have this relation, the problem basically solves itself, because you are an n squared solution is allowed. So you just go from all values of n to all values of n. So I just used the O of n squared solution. So let me just look at my implementation. Okay, so I was really helped a lot by this mod template that I have. And otherwise, like I couldn't just divide by 2 here. I would have to multiply with the mod inverse of 2 and again take the mod of the thing that is left. But since I have this template for calculation of all the modernums and all that, I can just divide directly. And the template has redefined what a division means for this mod integers. So I don't use vector of integers here. I use a vector of mod integers. So this is an interesting thing. So maybe I could link the template if someone requires it. So I input nm and k. I just have a dp. So I have a vector of vectors, and I could have done n plus 1, m plus 1, but I didn't care because n itself is 2000 and m is definitely less than n. I can just do an n square over here. I know that the dp of I comma I is definitely 0, and the dp of so this is just stupid here. I could have just said dp of I comma 0 is I times k. I just did it this way because I got confused. I thought that my mod integers wouldn't be able to handle multiplication or something, which was like stupid. After this, as I said earlier, dp of ij is dp of I minus 1 j plus dp of I minus 1 j by 1 j minus 1 by 2. And now don't print dp of n comma m, because you need to understand m is at least how many adds you want to have. So the number of subtracts that are allowed to you is n minus m. Just print dp of n. So you have n turns with n minus m subtracts left, and whatever the value is going to be your answer. So I felt that if you have a good understanding of dynamic programming, and if you're able to get the recurrence relation for this problem pretty quickly, then this problem is definitely going to be easy for you. It's not going to be really difficult. I think if D F1 would have been placed instead of C, and more people would have solved it. That is my guesstimate. But you could see that only 174 have solved it yet. So that is weird. For F2, now F2 is difficult. I must say. I must say that I found it to be difficult, but like the idea just clicked for me. Otherwise, I would not have been able to solve it during the contest itself. Okay, so what are we going to do over here? We clearly know that an n squared solution is not going to work here. We want to just have a O of n solution over here. So whatever dynamic programming just no brains it for you. I don't have to use your brain, just have to give it to the dynamic programming and say here you go, just solve it. But you can't do it this time. You have to just think about it now. So let's say I'm standing here. I'm at I turn with j negatives left. And what happens here is that using the same recurrence relation, I can see that half of my probability, like half of my value for the dp comes from I minus 1 comma j, and half of my value comes from I minus 1 comma j minus 1. So what I'm trying to do over here is a certain vertical represents a certain value of j for me here. So let's say it's j minus 1. I'll try to I'm trying to be just systematic over here so that it is helpful. Now, out of the half value contributed by this dp, another half value will be contributed by I minus 2 comma j. So half is one fourth essentially, and another one fourth value will be contributed by I minus 2 comma j minus 1. From this half, another half value will one fourth value will be contributed by I minus 1 j minus 1, and another one fourth value will be contributed by I minus 2 j minus 2. So what we have here is just basically a Pascal triangle. It's basically a Pascal triangle. So what is a Pascal triangle? So it is basically 1, 1, 2, 1, 1, 3, 3, 1. So you can observe, I'll change the color here. This is slightly confusing. Please try to understand. So this is 1, this is 1, 1, 1, 2, 1. So you can see that the probability that is provided that by this particular element is equal to, say, let's just call it depth, let's just call this depth I minus 1. So the Pascal triangle of depth I minus 2 and the second element of that divided by 2 to the power, uh, what would you call it? Um, 2 to the power of how many elements that there are here. So I think this is confusing. Let me try some other approach. So what I want to do is try to think of this as the first node of the Pascal triangle. So try to think of this as this. Okay, my Pascal triangle was wrong, unfortunately. It's 1 1. There is a 1 1 over. Sorry. So the second, these two guys are basically this. So we know that basically why am I saying 1 1 or 1 to 1 instead of 1 fourth and half? The value that is contributed by this probability is equal to the one that I have divided by the depth at which you are now. So for example, if you are at depth 1, so from I you went to I minus 1, that is a depth of 1. So you divide by 2 to the power the depth you are at. So the contribution by j would be 1 by 2 to the power depth. Contribution by j minus 1 would be 1 by 2 to the power depth. In this case, you know that the contribution would be 1 by 2 to the power 2, 2 by 2 to the power 2, and 1 by 2 to the power 2. This is how it works. So by this logic, you wouldn't need the assistance of dynamic programming to help you get all the states. You can directly, I'm going to the next slide. You can directly from dp of I comma j move to something like dp of 1 comma j. And dp of 1 comma j is something that I can, okay, why am I, nice slide. Okay, dp of 1 comma j is something I can pre-compute. Okay, dp of 1 comma j is something that I pre-compute. How can I pre-compute it? If I have j greater than equal to 1, I can surely say that if Bob has more negatives than the number of turns, everything is going to be a negative. So if j is greater than equal to 1, dp of 1 comma j is definitely going to be 0. Now for j is equal to 0, we have dp of 1 comma 0 equal to k. Okay. Now what is the issue that I'm facing here? The issue that I'm facing here is that suppose at some particular point I get dp of 2 comma 0. My answer should directly be 2k, but I'm not able to stop here because I do not have this state filled in. I'm directly going to dp of 1. So what I'm doing here is that I'm essentially extending the definition of the dynamic programming. So instead of just having dp of 1 comma 0, like dp for dp of 1 comma j for some positive value, non-negative value j, I'm also defining it for the negative values such that I'm able to get correct values for dp of 2 comma 0, dp of 3 comma 0. It is a bit complicated, but try to understand this. I don't care what the dp of 1 comma minus 1 is, because having minus 1 negatives has no meaning. But what I'm trying to do over here is I'm trying to define dp of 1 comma minus 1 in such a way that dp of 2 comma 0 doesn't lose its consistency. That is what I'm trying to do. So what would be the definition of dp of 2 comma 0? It would be dp of 1 comma 0 plus dp of 1 comma minus 1 over 2. Right? And since I want this to be 2k, I know the dp of 1 comma 0 is k. That gives me a value of dp of 1 comma minus 1 is equal to 3k. Okay, gives me a value of dp of 1 comma minus 1 is equal to 3k. Similarly, I would ask you to take some more examples. Try to take dp of 3 comma 0, dp of 4 comma 0, and try to have them have meaning here. Their meaning is derived by these units, which do not have any meaning on their own. There is no meaning that there is no meaning in the sentence that Alice will have one query and Bob will have minus one negatives to offer. It doesn't mean anything. But I'm trying to use them in such a way that these symbols have their original consistency. Okay. So if you try to do this, what you will find out is that dp of 1 comma j has a value of k minus 2kj. You will find this for j less than 0, less than equal to 0, I guess. And if for j greater than 0, you can just say that they are 0. This is what your dp is going to be. And now, since you have converted your dynamic programming into a single, you just need one variable, no? Just need to iterate over all of the j's. you have essentially solved the problem, which is a really good feat. So you need to know that you were initially at dp of n comma something. At the end, you are going to be at dp of 1 comma something. So you are going to essentially move n minus 1 different steps. Okay, you're going to move n minus 1 steps. So for n minus 1 steps, we are going to need the n minus 1th sequence. We want the sequence at the depth of n minus 1 in the Pascal triangle. So basically, let's have some slightly more info about a Pascal triangle. So let's say a Pascal. So I have a Pascal triangle over here. Okay. Okay. So what basically this represents is that these are the coefficients of the different elements at 1 plus x to the power 0, 1 plus x to the power 1, 1 plus x square, 1 plus x cube, and 1 plus x to the power 4. These are the coefficients of these different elements. Now, what we want to understand over here is that these coefficients can also be found out by the 1 plus x to the power n. This represents the nth level of the Pascal triangle. Pascal. And the value of the coefficient is going to be NCR. For you can also represent it by NCR. For example, if you want to generate 1331, this can also be written as 3C0, 3C1, 3C2, 3C3. Like 3C0 is basically 320 if you don't know C. If you don't know how C works. So what I want to do is, this is another useful thing from the template, that I find out the NCR for the depth. I iterate over all the different positions. Now what I do over here is this is calculation of J. Okay. If I find so J is basically n minus m minus 1. If you try to think of it in coding terms, and if j is positive, I don't need anything. Like, this is not going to give me anything, so I essentially just output a 0. If j is negative or 0, I use the same formula that I told you earlier, which is k minus 2kj. You have to represent it in this way, and I just multiply it with that. So basically, dp of ij would be k minus 2kj times the value of the Pascal triangle. But since I told you it's not just the Pascal triangle, it is Pascal triangle divided by 2 raised to the power height. I will just keep on dividing it by 2 raised to the power height. And please remember that if you just divide it this way, you're not going to get a correct answer. This division is only given to me because I'm using mod integers and using a special mod template. Otherwise, you would have to use a mod inverse or something. And I really suggest you to have a template for mod inverse, not just like code it on your own. It would be really difficult. And then I just print answer. And thus I complete all the problems. I looked at E, but I don't really have a solution in mind. I need to think more about it. But I hope that A to D and F1, F2 are helpful for you. Thanks for watching this.